And then the first question or the first idea for the askathon would be to discuss this task here. Some schematic, not really from our exercise booklet, but something that would be fitting to what we have done. A circuit with 2 voltage sources and in total 5 resistors. Looks a bit hand-drawn because the resistor symbol here is a different symbol than there, but okay. And so the task here is to use nodal analysis to find the current through this 4 ohm resistor, through this resistor here at this position. So I will try to copy this and paste it into my drawing program. And first thing that I would like to do is to add these soldering dots here each and everywhere, because from my point of view they are really missing and are important. And then let's say and let's define that that the current through this 4 ohm resistor that we are looking for, that it should point into this direction. It's more or less some arbitrary choice, but okay, so this is the current that we are looking for. And we should use nodal analysis to do this. And the problem here with using nodal analysis at first glance is that we have voltage sources. It would be much easier if we have current sources, but unfortunately we have voltage sources. Luckily, this voltage source here is a voltage source with some series resistor. So this is something, what would you suggest?
We can find the current through.
Yeah, we could convert this into a current source. So we can convert this into a current source, and we have a current source here, no problem. Still, we could also, because this is also a voltage source with some resistor in series, we could also convert this into a current source, but then this resistor would behave different, and the current through this would be also a different current than in this case. Still it's doable, but still it's a bit different. So I would suggest we can do different variants. So I would suggest at first we leave this source as it is and just convert this source to a current source. So if I somehow redraw this circuit, so the voltage arrow here points in this direction. So if we convert this into a current source, the current would point into the opposite direction, so upwards. And this 8 ohm resistor here that is connected there in series would turn into a parallel resistor. And okay, I will also try to use these symbols here. So this is then the parallel 8 ohm resistor, and the remaining network stays as it is. So I will just copy this. So another 8 ohm resistor there. Then we have this voltage source. Maybe I need to move this a bit up. So here's our voltage source. I will redraw it using this symbol. Then we have the 4 ohm resistor, and then we have the other 2 resistors, and we could simplify them with some parallel circuit, but I would just also leave them as they are. And I see that I'm much better and quicker in drawing the German or European resistor symbols. These, to be honest, look a bit ugly, but okay. And so this resistor here is also 8 ohm. This is the 4 ohm resistor. We are looking for this current I. This is another 8 ohm, and this is the 6 ohm resistor. Okay, so we just converted this voltage source into a current source. First question would be, how large is this source current here? How can we calculate this?
The V over R.
Yeah, the voltage divided by the resistance just using Ohm's law, so 24 volts divided by 8 ohm. 8 ohm is volt divided by ampere, so the volts will cancel each other. We are left with the unit ampere for current, and 24 divided by 8 is 3 ampere. Okay, so this is 3 ampere here pointing upwards. So then the next step of nodal analysis would be
to label the nodes.
To number and label the nodes. And so we have also this voltage arrow here from this source. And now to make things a little easier, we have a free choice where to place the reference node. And so we could place the reference node here, we could place it there, we could place it there. I would suggest to place the reference node here, because then this, if we, for example, number this node here, this is all one node. If I label this as 1, okay, then we have some nodal voltage that goes over this resistors here, for example, from this node to there. This would be the voltage 1, 0. And if we label this node as 2, then we have some voltage going from here to there, voltage 2, 0. And we have this last voltage here, V3, 0, but we already know this, it's 4 volts. So it's quite convenient to use this as a reference node and maybe to use this one as the last node, because then we would end up with some equation system of 3 equations and 3 unknowns, but 1 unknown is actually already known because it's the source voltage.
Can I ask?
Sure.
When we change the voltage source into a
Current source,
the 8 ohm, the one that was in series became parallel.
we can just move it into a parallel circuit or into a parallel resistor. Still, it will be the resistor has the same value, but it will behave different. There will be a different current through this resistor and a different voltage and so on. There must not necessarily be the very same current and voltage through this resistor as before. That's why it's not a good idea to convert this into a current source. Okay, so next step would be to write down from my point of view, next step would be to write down nodal equations or Kirchhoff's current laws for the remaining nodes, and these nodes are labeled with 1 and 2. So if we check here, and maybe I will use different colors. So we have a current here, we have a current there, we have a current here and there. And I will just call this here I1, I2, I3, and I4. And the nodal equation then at this node would be that the sum of these 4 currents must be the same as the source current on the other side, because they are all flowing towards the node and this one is flowing away. Okay, and so if we do the same thing here for this node, then we have our current I that is flowing towards the node, and these currents are flowing away. So this time I will write I minus I3 minus I4 equals 0. Why do I write this on the other side? Because this is a known quantity. All the other quantities are unknown. So I've ordered this a little bit in a way that these are the unknown currents, these are known currents. Okay, so the next step inside these equations would be to replace the currents by voltages. And so if I once again start with 1 or do it for 1 and 2. So this current depends on this voltage times, or no, divided by this resistance. So here we have V12 divided by 8 ohm. This is this current, but with a minus because current and voltage are pointing in opposite directions. So here across this resistor we have the very same voltage, so minus V12 divided by another 8 ohm. So then we have this current here, and yeah, so here I will introduce another voltage and say this voltage from here to here, for example, would be the voltage V21, and the voltage V21 later on can be calculated from V20 minus V10. Right? If we want to have this voltage, we can take this voltage minus this voltage, then we end up with this voltage here. So now it's plus the voltage V20 minus V10 divided by 8 ohm, and plus the same V20 minus V10 divided by 6 ohm. And on the other side we have I source, this is 3 ampere. And for the second equation, this current I is still unknown. It's 1, no, it's not 1, it's I. Yeah, okay, but okay, for this current we still need something. For this current we need the voltage drop across this resistor here, because otherwise we have too many unknowns in our circuit equation, and this voltage here would be V32, and V32 is the same as V31 minus V21, and V31 is 4 volts, so it's 4 volt minus V20. Okay, so then this is what we can insert in our into our equation. So this is 4 volts minus V20 divided by this 4 ohm resistor here. Yeah, and then I can more or less just copy the other equations here, but just with a minus, so minus V21 minus V1, or V20, V10 divided by 8 ohm, and minus V20 minus V10 divided by 6 ohm. And this at the end should be 0. And because the 4 volt divided by 4 ohm, because this is known, I would move this to the other side. So that on this side we only have unknown quantities, and on this side we have the known quantities. So I will skip this here, or let's say skip it here, and say this is minus 1 ampere on this side. So this should fit, and now we can check. I mean, now we have set up some system of equations with 2 equations and 2 unknowns, namely V12 and V10 and V20. So our 2 nodal voltages that are unknown. These are the 2 unknowns in this. And so the next step would be to write this system of equations in matrix form. And I will probably use the space here. So we have the matrix with the coefficients, and then we have the vector with the two unknown nodal voltages, V1, 0, V2, 0, and on the other side we have the known quantities, and the known quantities are just 3 ampere and minus 1 ampere. And yeah, so now this using these fractions here, it's not very convenient. So instead of 1 over 8 ampere, instead of 1 over resistance, I will use a conductance. So this is, okay, at the end we will probably stick to a fraction. No, it's 0.125 Siemens, but the 1 over 6 is not that convenient, right? Because 1 over 6 ohm is 0.166 Siemens. Yeah, but maybe it's still nicer to write it in Siemens. But we can check. So here we have if we look what everything that is associated with the V1, 0 is minus 1 over 8, minus 1 over 8, another minus 1 over 8, and another minus 1 over 6. So minus 1 over 8, minus 1 over 8, minus 1 over 8, and minus 1 over 6. My drawing pad is lagging a bit. And what is associated with the V2 is plus 1 over 8. And then we see, okay, it would probably have been a good idea to just multiply this whole equation with minus 1, and then this would turn into a plus, 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 and plus. This would turn into a minus, and this would also turn into a minus. And then we can do some check later on if this makes more sense to us. And so in the second equation here, if we check what is all associated with V1, 0, then it's plus 1 over 8, plus 1 over 6.
For the first time, for V2, 0, it was 1 over 6.
Yeah, 1 over 6. Here, right? Here it's also 1 over 6, and we have another 1 over 8 here, right? So it's also minus 1 over 6 over there. Very good point. I've just omitted the sign to change it later on. And so if we check then with V2, 0, we have 1 over 4, or minus 1 over 4, minus 1 over 8, minus 1 over 6. So minus 1 over 4, minus 1 over 6, minus 1 over 8. And so also here I suggest to make things more easy and understandable to multiply this equation also with minus 1. So this will be minus, minus, plus, plus, plus. And the unit of all this is Siemens. I will add the Siemens here later on. And okay, so now we have just converted this system of equations in usual form into matrix form, changed the sign a little bit. And so now we can further check this a little bit because we somehow remember the rules for the nodal voltage analyzers. On the main diagonal of this matrix, there was always the sum of the conductances that were connected to a certain node. So at the first node, we have the sum of this conductance, this conductance and this conductance, because they are all connected to this node. On the second node, we have the sum of this conductance, this conductance, this conductance, because they are connected to this node. Makes sense. And on the off diagonal elements, we have the, let's say, coupling conductances between two nodes, and between node 1 and 2, we have these two. And they were always plus, they were always minus, so this totally makes sense. And on the first node, we have this source connected, flowing away from this node. That's why it's minus. And at this node, let's say we have this source connected with this resistor. 4 volt divided by 4 makes this 1 ampere, and it's also, yeah, so here I think it does, okay, I need to change the sign here, right, from minus into plus, because this at the end would flow towards this node. So good that we checked, that we found this error here, this mistake in the sign. And so, yeah, then the last step. And greetings back to Dresden. Alexander Lasch is just a comment in the chat. So then we go into Octave. I make this window a bit smaller, so that everything here fits on the screen. And we can say nodal voltage analysis matrix will be 1/8 plus 1/8 plus 1/8 plus 1/6. Then minus 1/8 minus 1/6. And in the next row we have another minus 1/8 minus 1/6 and plus, well, I can omit the plus, 1/4, 1/6, oops, plus 1/8. This should be our matrix and looks more or less meaningful. And then we have this source vector, and the source vector is -3 and +1. And then we can get our nodal voltages, and the nodal voltages we get from the reciprocal of this, or the inverse of this matrix, better to say, multiplied with the source vector. So we have this left division, and then we get 2 nodal voltages. And so then the last step, if we want to know this current here, so we can go backwards. This current should be, if I switch back to blue, this current should be this voltage that we just calculated multiplied with the 4 ohm. And so, yeah, it's the 4 volt minus V2 0, or the second nodal voltage, and then multiplied with 4 ohm. And so now if we do this and say our current that we are looking for is 4 volt minus the second of these nodal voltages, and then this multiplied with 4 is...
Why not divided?
Why not divide? Yeah, good question. I think you are totally right. I is... Otherwise would be quite high value. So 1.4 ampere, this obviously totally makes sense. Yeah, and so now we could do a quick check and calculate with the other voltages that we know, the other currents, and finally also check that each Kirchhoff's voltage law fits, but it should, because we have calculated the voltages in this way, but that also all the Kirchhoff's current laws fit. What I would suggest instead is to use LTspice, the LTspice circuit simulator that is hopefully found here in, there's the desktop app, and the computer is super slow. And I don't want to do an update right now. I will just open up a new schematic. The voltage source can be found under component and voltage. So we need one voltage source here, and with Control R I can rotate, and we need another voltage source there, and then we can place one resistor here. I will move it or rotate it another time. So current here should be pointing to the right, current here should be pointing downwards. Here the current should be also pointing downwards, and if I want to have a current through the right, then it should be like this. So we have all the elements. I will place the reference node here on top and take the wire tool to connect everything together. And draw the outer loop first, and as you draw, these soldering pads at the elements disappear, and if we draw some connection, then some node should appear here and there, and this also happens. So this should be our circuit and the original circuit. And I can label the nodes and label this node here as 1 and this node here as 2, so that we also directly get the nodal voltages. I could also label this one here as 3. And now we need to set the value, so this should be 24. This should be 4, and this should be 8 ohm, this should be 8 ohm, this should be another 8 ohm, this should be 6 ohm, and this should be 4 ohm. And then we should be more or less ready to go. So if I hit run and we want to just calculate some DC operating point, and it's calculating, and then we get some result here that I will make a bit smaller and try to also find the Octave window and make this also a bit smaller, so that we get here everything on one screen. So the nodal voltages that have been calculated in Octave were minus 6.4 volts and minus 1.6 volts. So these are the same values that we get here, and the last nodal voltage is 4 volts that we have not calculated because we already know this. This was our source voltage here, and the current that we just calculated, this current here with the 1.4 ampere, is the current through the resistor R5. And this also is the 1.4 ampere here, which totally makes sense. So yeah, this is a nice and also correct solution for this task here using nodal voltage analysis. So what we can do now is I will open up a new node and paste this in again, and we can try to do a second variant And the second variant is we replace this source here. I will redraw it. We will replace this source with some current source. And we will also replace the other source here with some current source. And then, yeah, something will happen. So I mean, here it will be the same as before. Here it will be also a 4 ohm resistor, but if we want to know this current here still, and we will see in the redrawn schematic that's kind of a different current there. Not only the current just through the resistor. So if we redraw the circuit, we have a current source, and this current source, as mentioned once again, is pointing upwards, and as we discussed before, this was 3 ampere. So now, if you allow me, I will use the German European resistor symbols. So this is 8 ohm, and so this is the redrawn blue part of the circuit. Then we have another 8 ohm resistor. This is the original 8 ohm. Then we have this green part of the network, and the green part of the network now is also converted into a parallel connection of a current source. And the current source, if the voltage here is pointing in this direction, the current source will also point in the opposite direction, so to the right, and this is the converted 4 ohm resistor. So this source current here is 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 another 4 volt divided by 4 ohm, and this is 1 ampere. And the current that we are looking at is this current here. This is the current we are looking for. And as we can see, it will be, it's the sum of the current through this resistor plus the source, not just the current through the resistor. And then we have the remaining part of the circuit, which is an 8 ohm resistor and a 6 ohm resistor. So this completes the circuit. Some soldering dots each and everywhere. And now it should be fairly easy because we have just current sources to do the calculation here. So this is another 8 ohm. And this is 6 ohm. Okay, so now I would suggest to, as usual, for example, say this is the reference node at the bottom, this is everything here is node 1, this is node 2, so we can set up system of equations directly in matrix form, and we have this matrix of the coefficients, this multiplied with the unknown nodal voltages V12, V10, V20 gives the known sources. And so now we can check at node 1. The resistors that are connected at node 1 is this, this, and this. So here we have 1 over 8 plus 1 over 8 plus 1 over 4. The unit everywhere is Siemens. At the second node, we have 1 over 4, 1 over 8, 1 over 6. 1 over 8, 1 over 6, plus 1 over 4. And the connecting conductance or connecting resistance, coupling resistance between this node and this node is 4. So it's minus 1 over 4, minus 1 over 4 here. So then we can check the sources that are connected at this node is plus 3 ampere flowing towards this node and 1 ampere flowing away. So it's 3 minus 1. The unit here always is ampere. And at the second node, we just have this source flowing towards the node, the 1 ampere. So this should be our system of equations. And yeah, with this we can calculate this nodal voltages in a second, once again using MATLAB or Octave or whatnot. And so then if we know, let's take a different color, if we know this voltage here, which is the voltage V12, we can also calculate this current, IR. And then our unknown current here should be the sum of IS, this IS plus this, plus the IR, right? And this voltage here, V12, will be once again V10 minus V20. So this is the way to go. If we change to Octave, and if I do some CSC and some clear all maybe, then we can start with our nodal voltage analysis matrix and say this is 1 over 8 plus another 1 over 8 plus 1 over 4, then minus 1 over 4, and in the second row another minus 1 over 4, and then 1 over 8 plus 1 over 6 plus, not enough space, plus 1 over 4. That's the matrix. In the source vector, we have 3 minus 1 and 1, yeah, which is 2 and 1 at the end. And then I can copy this equation to calculate the nodal voltages. And we remember, okay, 6.4 I think is something that we had before. And so now if we use yeah, if we use try to use the equation on the top, so the current is, the source current, this is 1 ampere plus the current through the resistor, and the current through the resistor is from the nodal voltages, the first one minus from the nodal voltages the second one, but this of course in parentheses, and this divided current is voltage divided by resistance, let's not do the same mistake as before, divided by the 4, and so we get 1.4 ampere, which totally makes sense and which also coincides to what we calculated before. But let me at first draw down or note down the result here, 1.4 ampere, and this coincided to what we calculated here, and this also coincided to what we calculated using LTspice. So yeah, if you know what you are doing here, if you are not get fooled by this mistake of that this resistor will behave the same as the same resistor before, so that this current that we're looking for is the sum of these two currents here, then this is probably the way to go. This is probably the simplest solution for this task here.